Hey guys, here I am with a new episode of Topic Talks and I welcome you all to Science Gurukul. My name is Bhaskar Mishra and the topic which I have chose for today and for some of the upcoming episodes is Noether's theorem. We will also be covering some of Lagrangian mechanics in the upcoming episodes to understand the mathematical aspect of Noether's theorem. This theorem was proposed by Noether, and she was a mathematician, and this theorem is considered to be one of the most beautiful theorems in physics. It basically links two things. One is symmetry and other thing is conservation laws from physics and symmetry from mathematics. So basically you can say the beauty lies in the way this theorem connects maths to physics. Okay, so we will be moving towards the statement. The statement goes as that if we have a system which is being acted upon by conservative forces, and if you find any continuous symmetry in that system, then for sure that continuous symmetry will be corresponding to a conservation law which will be applying in that system, or to a quantity which will be invariant in that system. Okay, for example, let us take the systems which I'll be considering further in this video. All of them will be acted upon by conservative forces, right? There will be no non-conservative force acting upon. Okay, so if we talk about rotational symmetry, if rotational continuous symmetry is present in the system, then in that case the angular momentum will be conserved. If translational symmetry is present, then the linear momentum will be conserved. And if time is invariant in the system, then energy will be conserved. So in this way, the theorem has some examples. In this way, the theorem works actually. So there are two things to be understood if you want to understand this theorem completely. The first one is symmetry and the second thing is conservation laws. Okay, so let's move towards symmetry. Symmetry, we need to understand it mathematically. First of all, let's take it in general terms. Suppose I have an object O and I bring some transformation which makes this object O dash. If O and O dash are same or you cannot distinguish between them, then you say that this transformation is symmetrical. This function is symmetrical, this operation is symmetrical. Now let's move towards the formula. Let's move towards a function, say y is equals to x square, right? Y is equals to x square. So when you plot the graph on the Cartesian coordinate, then you will see that the graph is parabolic and it has its vertex at origin, that is 0, 0. And now I bring a transformation in this function. I transform x to minus x. Okay, I replace x by minus x. So now my equation will be y is equals to minus of x whole squared. Okay, y is equals to minus of x whole squared. Now if you plot this function on the graph, then you will be having the same parabola drawn with its vertex at 0, 0. All the characteristics of the parabola will be same. You won't be able to distinguish between the two graphs. Hence you will say that this transformation is symmetrical. This function y is equals to x square or y is equals to minus of x whole squared, this is symmetrical, right? So this is the mathematical aspect of symmetry. Now symmetry is of two kinds. Okay, symmetry is of two kinds. The first one, which is actually dealt in our Noether's theorem, it is continuous symmetry. So let us take this ring. Okay, we have this ring, right? Now I am rotating this ring. Okay, about this axis I am rotating the ring. Okay, the ring is rotating, right? Now there are many states, there are infinite states that the ring is passing through, and you are not able to distinguish between any of the states. All of the states are looking same, right? So this ring is having a continuous rotational symmetry. Now if I talk about discrete symmetry, so let us take this remote. Okay, so better than ignoring, let's take this. So here you see a rectangle. Okay, in this view you see a rectangle. Now I am rotating it. Avoid this line, assume it to be a complete rectangle. You will see now the state which has been attained is identical to the initial state, right? The state which has been attained now is identical to the initial state, which was 180 degrees before this state. In between we had many transition states which were not appearing to be symmetrical, which means that in all of these states, this system is not symmetrical. It is symmetrical only in some of these states, and in between those states there are transition states, right? So this is known as discrete symmetry. It is not throughout symmetrical, it is not continuously symmetrical. So this is known as discrete symmetry, right? So this was the symmetry which Noether was talking about. She was talking about continuous symmetry in her theorem. If there is discrete symmetry present in the system, in that case Noether's theorem won't apply, right? And if there is continuous symmetry, then the Noether's theorem will apply. And once again I will be repeating the examples, and we will be concluding today's video, as we have discussed the basic aspects of Noether's theorem statement, right? To understand, we will be making many more videos further. The next episodes of Topic Talk will be based on Noether's theorem, and for that we need to understand Lagrangian mechanics. So in the next episode we will be covering Lagrangian mechanics. So once again we will revise the examples of Noether's theorem. For example, if there is a rotational continuous symmetry present in this system, this corresponds that there will be the angular momentum will be conserved for the system, right? And if there is translational continuous symmetry, the linear momentum will be conserved. And if there is time invariance, which means time is not varying, in that case you will have the energy conserved for the system. So this was the statement of Noether's theorem. Here we conclude today's video. And one more thing which needs to be discussed. We saw that if in system the symmetry is present, then any quantity, a particular quantity is conserved. But the vice versa is also true, right? The vice versa is also true. If a system is being acted upon by conservative forces, and if any quantity is conserved, if there is any invariant in that system, this also corresponds that there would be continuous symmetry, some sort of continuous symmetry in the system. So this was the statement of Noether's theorem, guys. I hope this would have been helpful, and if you found it to be helpful, do like the video, share it with your colleagues, and subscribe my channel. This will help me a lot. Let's meet in the next video. Jai Hind.